Okay, we're going to do a video tutorial in SPSS on how to run a simultaneous multiple regression. The DV, or the criterion variable, that's the one we're going to try to predict with our model, is how many times a celebrity can be expected to be married in their lifetime. That's our DV marriage frequency. And the three predictor variables are monthly income, the number of previous romantic relationships they had, and the number of parties or events that they attend per month. So we're going to try to use those three predictor variables to accurately predict how many marriages any Hollywood celebrity can expect. The first thing we're going to do is screen the data. All right, first step, go to data view. We're just going to give this a visual check to see if there's any missing values in any of our variables. So there are a few missing values here. Yeah, there's a couple missing on the bottom. So we do have some missing data. Okay, because there's so few missing pieces of data and our sample size is 156, we're not going to overly worry about what's missing. We're going to go ahead and let the SPSS program handle it. To check normality on a multiple regression model, we're going to use the Mahalanobis distance formula. So to do that, we're going to go to Analyze, Regression, Linear. Okay, so our dependent variable is our criterion variable. It's the number of times they were married. These other three are the predictor variables. They're going to go in there. And we go to Save. Click the Mahalanobis box. That's going to do the measuring of the residuals for us. We're going to click Continue. Click OK. Even though there's a bunch of output boxes for SPSS, we're not going to look at any of them except for the residual statistics box. Remember, we're just checking for the normality using the Mahalanobis. So the Mahalanobis distance, the critical value is about 20.2. So we're going to compare that to a critical Mahalanobis distance table to compare our maximum number to what they consider a critical value. Okay, this is a Mahalanobis calculation critical value sheet. It should be on the course somewhere, look around. So we're going to use an alpha of 0.05. And N is the number of sample size, which is 156. K is the number of predictor variables, which is 3. We should be ready to go. Hit enter. Bam. So there is our critical Mahalanobis distance. So our maximum is higher than that. So we have to go back and identify whichever subject has a Mahalanobis distance of greater than 18.6 and delete them from the study. Okay, so hold on while we get set up. Here's the fastest way to delete those Mahalanobis numbers that are over 18.6, whatever it was. We're going to go to Data, Sort, and we're doing the Mahalanobis. We're going to start with the largest going to the smallest. Click OK. And then let's get back to our data sheet. And it put it in the right order. So it looks to me like we do have two subjects that are outliers. Okay. This is greater than 18.6. This is greater than 18.6. So what we're going to do is delete them. Just highlight them and hit delete. Go back and make sure they were deleted. And they were. So now our data is normal. Next, we're going to check the assumption of linearity using a scatter plot. So we're going to go to Graphs, Legacy, Scatter / dot, Simple, Define. So what we're going to do is compare. We're going to do a scatter plot between each IV separately with the DV. The DV is always the y-axis, and that's the number of times they've been married. So we'll start with the number of previous romantic relationships they had. Ooh. And then we're going to click OK. So let's take a look at that data. All right, you got to double click on the graph. We're going to add a trend line in there. Use that little fella. And so there's our line of regression, and there's our R squared up there. All right, Be quiet, Copilot. All right, since r squared is not equal 0, then we did not violate the assumption with the first ID. So we're going to do this with all three of them. Okay, so there's the first one. Let's go back and redo the second one. Graphs, legacy, scatter, simple, define. We're going to switch IVs. So let's kick out the number of previous relationships with the number of parties and events. And click OK. So there's that graph. Let me pull it up for you. We're going to double click, add the trend line, click closed. And again, the r squared is not 0, so we did not violate the assumption of linearity. We're going to do this one more time with the last IV. Graph, legacy, scatter, scatter. Define, out with the party people, in with the monthly income. Click OK. Get the new graph. Hold on. Double click. Add trend line. Close. And this one's got a pretty big r squared, and it's not 0. Okay, so the assumption of linearity has not been violated. We can move on. Okay, now we're going to check the assumption of independence of observation, also called independence of sampling. With multiple regression, it goes by the name of autocorrelation, and it's a bad thing. So what we're going to do is we're going to look at it through the eyes of the Durbin-Watson test. So here we go. Go to Analyze, Regression, Linear. Okay, and our DV was the number of times they were married, and all the other ones except for the Mahalanobis were the IVs. We're going to go to the Statistics button, and we're going to just look at the Durbin-Watson. Okay, just click the Durbin-Watson. That will tell us if the data is autocorrelated or not. If it is, you're in trouble. So you're going to click OK. And then here's Mr. Output Sheet. And again, we're just looking at the Durbin-Watson output. All right, so let me center this for you. All right, so there's our Durbin-Watson test statistic. So, importante, this Durbin-Watson number should be somewhere between 1.5 and 2.5. I will repeat that. This Durbin-Watson number should be between 1.5 and 2.5. That means that there is no significant autocorrelation with this data. So in other words, according to our data number here, we do not have autocorrelation. So we are going to press on. Okay, on to the assumption of homoscedasticity. Go to Analyze, Regression, Linear. All right, it's preset from the last time we got our DVs and IVs in place. You're going to go to Plots. Okay, your Y variable is always your dependent variable, and that is your Z residuals. In this test, the residuals are always the Y-axis, and your predicted is the X-axis. We really don't need a histogram here, and we're just going to click Continue, and then OK. And we should be getting those graphs. Here's one. Give me a second. Let me pull it up for you. Okay, there is a graph. We're going to double click. We're going to add the add fit line. Does it automatically? Just close that out, and it's going to put that in there. So now we have to decide, is the data symmetrical? In other words, is half the data on top reflected by half the data on the bottom? Okay, looking at the graph here, the line, it's not 100% easy to tell if this data is homoscedastic or not. Okay, right? There should be a mirror image of the points above the graph with the points below the graph, so it's not clear. So we're going to try something different. It's called the Loess line. I don't know if I'm pronouncing that right, but let's see what that looks like. All right, double click on the graph again. We're going to go back up to the same place. We're going to add the best fit line. Bam. This time we're going to click the lowest line. Normally, if you've already stuck in one line, the lowest line should automatically pop up. And it did. So we're going to click close. So now we're looking at the lowest line. It's that weird little curvy thing here. It looks like we may have violated the assumption of homoscedasticity, because if there was no homoscedasticity, this lowest line should be relatively flat and parallel to this straight line in here, to the best fit line. So it looks like we did violate the assumption of homoscedasticity. But this is a very, very robust test, so we're just going to press on and keep going. So hold on. All right, the last assumption is multicollinearity. What we're going to do, though, is we're going to go ahead and run the regression, because SPSS will go ahead and spit out a multicollinearity test statistic, and that will tell us if our data is violating it or not. Okay, so we're going to go ahead and do that first. So here we go. Analyze, regression, linear, regression, linear. Okay, our DV is set up, our IVs are set up. So let's see what we can do here. We go into the statistics. We like the descriptives, part and partials, collinearity. And here's the box that will give us the multicollinearity assumption check. Okay, make sure you check that box. Click continue. Need anything here? Nah, we already did that. Don't really need a histogram. We already did the Durbin-Watson. Anything under options? All right, remember we had a couple of pieces of data that were missing. So SPSS is automatically going to exclude case list-wise, but just double check to make sure that that little button is clicked. Okay, so if it's missing a piece of data, it's going to drop that subject from the study. And again, since our sample size is so large, it's not really going to affect the results that much. So click continue, and I think we're ready to go. Cross your fingers, click OK. All right, now it's time to interpret our simultaneous multiple regression. First box, descriptive statistics, gives us the means of each variable, standard deviation, the number in each variable. So we started with 156 and we ended up with 151. So we threw a couple of them out because they were identified as outliers by the Mahalanobis test. And then there were a couple with missing data, so they just deleted those case-wise. But we still have a big sample size. Number box 2 is the correlation box. Now, everything that is done in multiple regression is going to be based on these correlations. But what I'm looking at is the significance between all the variables. Every one of them is significant here. Okay, so we have a huge significant correlation going on here between all of the variables. But let's go ahead and interpret what this output says. Okay, this box tells us that we ran a simultaneous multiple regression. If it was hierarchical, there would be a model 1 and a model 2 and a model 3, etc., etc. Here, if it was a stepwise, it would say stepwise underneath the method part. Okay, so looking at this, this is just a simultaneous multiple regression. We just threw all the IVs in at once. All right, so here is our R square. What this tells us is that this multiple regression model can basically explain right around 32% of the variance in the DV. So 32% of the time of how many times these guys have been married can be explained by our model. And that's pretty strong. Again, there's the Durbin-Watson test, which means that we did not violate the autocorrelation or the independence of observation. Here is our ANOVA. What this is doing is it's checking the regression against 0. So what this says is that there's a significant difference between the regression of this model and 0. So it means we have a significant regression. And then here's your money box right here. All right, the coefficient box has all the information we need. So the unstandardized coefficient, that's your B weight, the capital B. These are in units of whatever the IV is. So the monthly income, this you're talking about millions of dollars. This is the number of previous partners. This is the number of months or how many days or how many parties, okay? So just remember, unstandardized coefficients are B weights measured in whatever the variable is measured in. This is what we want. This is your beta weight column. This is breaking down each one of the predictor variables, the IVs, and will tell you how significant it is at predicting the DV. So it's gonna rank these things in order as to how much they affect the criterion variable. Or to put it in our terms of our problem, it will tell us what order of the IVs are strongest at predicting the number of times these celebrities will be married in their lifetimes. So, right, a beta weight of 0.5, that is obviously the strongest player, and it is significant. So the number of previous relationships they had, their beta weight is very small, their t-test score is not very big, and their significance is not less than 0.05. So in other words, it didn't matter how many previous partners they had or how many times a month they go out to parties or other events. The significance there is not less than 0.05 either. So in a nutshell, it took the three IVs and it ranked them, and according to our data, the only one that is effective at predicting the DV outcome is how much money they make in millions of dollars. All right, almost done with this video. Now we're going to talk about the partial and semi-partial correlations. So what that means is the partial correlation of each one of these IVs. So the monthly income, the partial correlation is 0.269. What that means is that IV can explain about 26.9% of the variance on the DV when the other two are controlled. So this number, 0.049, it's not very much. What that means is about 5% of the variance in the DV can be explained by how many previous partners they had when the other two variables are controlled, etc., etc. But again, you'll look at them. The only one that's worth a darn is the monthly amount of money they make, okay? So now, and that's the partial. Okay, so in SPSS, part means semi-partial. So what that means is that this number here represents the amount of variance of the DV that can be explained specifically by this IV with the other shared variance of the other IVs removed. I'll say that again. The part, which is the same as semi-partial, gives you the amount of variance of the DV that can be explained solely by each of these IVs, okay, with the other IVs' influences removed. So that's what the partial and semi-partial means. And again, the only one that's really significant is how much money they make, okay? The last thing we're going to talk about is, the next to the last thing we're going to talk about is the collinearity statistics. Remember, that was one of our assumptions, was no multicollinearity. And we do not have that here. How you check is, they're two different tests. They basically mean the same thing. But tolerance, if this number was less than 0.01, you would have multicollinearity. Yes, 0.01. If this VIF number was greater than 10, then you would be suffering from collinearity, okay? So they're inverses of each other. But we're good to go. We did not violate that thing. Okay, so we got one more little thing to do, and we're done. So please hold. All right, the last thing we're going to show you here is how to write out the actual prediction equation using the unstandardized B weights. Okay, so your Y hat, or your predicted Y, your predicted number of marriages will equal 0.536 times X1, and X1 is how much they make per month, plus 0.015 X2, and that represents how many partners they had, plus 0.003 X3, how many parties they attend per month, minus 0.286. So that is the official predicting equation. But now you look at these unstandardized B weights, the number of parties they attend, it's not going to influence the outcome much at all, because the coefficient here is practically zero. And the same with the number of previous partners they had. this factor is practically zero. So these bottom two IVs, they're not going to contribute much at all, which we already knew from beforehand. And there it is. And we are done. MGZ and Dr. Zhao out. All right, hold on. All right, we now... Shit.